When solving quadratic equations, in many scenarios, we have to take the square root of both sides to isolate x. The square root is the inverse operation of an exponent of 2. That's how we will cancel it out. And when we do that, we are presented with a number that is in radical form. And this video will be focused on how do we simplify that number that is in radical form. There are two approaches to this, so I will let you decide which of the two approaches you prefer. The first one, so your first option, is your prime factorization method. I will do a side-by-side example in the how-to. So we'll look at an example like the square root of 72. The first thing you do is you break down 72 into its prime factorization, meaning you're going to write 72 as the product of all prime numbers. And what's often used in this method is a factor tree. So to show you what that would look like, I want to break down 72. So I say, what number could I divide 72 by? Well, 72 is even, so I can break it down by dividing by 2, and I get 2 and 36. So I'm going to create this tree, so I'm drawing these little branches that show the breakdown. 2 is prime, so I can't break that down any further, but 36 is also even, so I can break that down. 18 is even, and 9 is divisible by 3. If it helps you, when you break down a number, you can cross out that number to avoid considering it for this next step. So you can see that we've broke down 72 into 2 times 2 times 2 times 3 times 3. Once we've broken down into the prime factorization, we are going to group repeated factors. I'll say prime factors, actually. In pairs. So, 2 repeats, 3 repeats, and I'm going to pair them up. So I have one pairing of a 2, and I have one pairing of a 3. That other 2 cannot be paired with any other 2, so it's going to be remaining ungrouped. Once we've made our groupings, we are going to remove the grouped number once per grouping. From the radical. If you have multiple groupings, multiple numbers to remove, you multiply them together. So I have one group of 2, so I remove 1, 2. I have one group of 3, so I remove 1, 3. There were multiple numbers I was removing, so I'm going to eventually multiply these together. Anything that did not get grouped, we put back underneath the radical. And again, if you have multiple numbers to put back underneath, you just multiply them together. In this problem, we only have one number to put back underneath, and that is that ungrouped 2. Carry out the multiplication that's necessary, and we get 6 root 2. And that is our simplified form of square root of 72. Now, why does this grouping method work? Well, we said square root of 72. We can write that as 2 times 2 times 2 times 3 times 3, which can be rewritten as 2 squared times 2 times 3 squared. Right? By writing it as squared, I'm essentially grouping in pairs. So why is grouping in pairs important when it comes to a square root? Well, we've already mentioned that the square root is the inverse operation of squaring something. And using radical properties, you could rewrite this thing like the following. So by grouping in pairs, which is essentially writing that number squared, I can see that the square root will cancel with that square. So square root of 2 squared is 2. Square root of 3 squared is 3. And then when it comes to the order of multiplying real numbers, that is a commutative operation, meaning the order doesn't matter. So I can do 2 times 3 and get the same result. But going through that process is unnecessary when I have this prime factorization method. But that is why it works. So I just wanted to show that. I'm essentially grouping in pairs so that when I take the square root of that pairing, it cancels out because that pairing represents that number squared. Now let's put this method to the test on a couple other examples. So let's say I have the square root of 8. I'm trying to simplify this, and we're using this first option. I break it down into a prime factorization. I then pair up any repeated prime factors. And again, before you do that, if you want to cross out anything you've broken down to avoid considering it in the pairing process, you can do that. I have one pair of 2's. Once I've identified the pairings, I pull that number out once per group. So there's one group of 2. Anything that did not get paired up goes back underneath the square root. And that thing that goes back underneath is this sole 2 that's off to the side. And there is the simplified form of the square root of 8 using the prime factorization method. Let's look at the square root of 405. 405 is not an even number, but it is divisible by 5. 5's prime, so it can't be broken down. 81, most people would probably break it down into 9 and 9. 3 and 3, 3 and 3. I've reached all prime numbers. I'm going to cross out anything I broke down to avoid confusion. Then I'm going to pair up repeated prime factors. The 5 doesn't have another 5 to pair it with. I pull the pairings out once per grouping. So there's one group of 3 to the left, and then right next to it is another group of 3 for 2 3's that I pull out. Anything that I did not group goes back underneath the radical. I carry out the multiplication, and 9 square root of 5 is the simplified form of square root of 405. Then lastly, look at the square root of 30. I break this down. I notice that in my breakdown of prime numbers, there's no repeated prime factors, so I cannot pair anything up. No problem. Whatever is unpaired goes back underneath. There are 3 things that are remaining unpaired, so they all go back underneath, and I get the square root of 30 when I carry that out. But that's what we started with. So what's the lesson here? When you break it down, if there are no groupings to be had, then that radical was already fully simplified. So this is already a simplified radical. Now, prior to, let's add on one thing to our process here. Prior to the breakdown, so let's insert one little thing. Before we go through this whole process, it would be worth our time to actually check to see if what's underneath the radical is a perfect square. The reason why is, well, let's say that we have the square root of 121. Well, before I go through this whole breakdown, what if I just said, well, wait a minute, is 121 a perfect square? And you would say yes. And I can just immediately say, well, that's 11. And I don't have to do any of this long process by going through all the pairings and then multiplying them all out. Now, if I forgot to do that and I did this process correctly, I would still reach the conclusion that this thing should equal 11. But it is a time saver if we immediately check before we start this process, is the number I'm dealing with a perfect square? Now, speaking of perfect squares, that will bring us to method or option 2. Which is identifying perfect square factor. So step 1, find the largest perfect square that the given number is divisible by. Write the factorization using that perfect square. That's step 2. So we're going to use the exact same example so you can see how this could be used either way. Let's say I'm looking at square root of 72 again. I'm asking myself, if I want to use this method, if you're familiar with the perfect square, so if you know the perfect squares, this can be an efficient method for you. If not, use the prime factorization method. What is the largest perfect square that goes into 72? Well, the perfect squares, 1, 4, 9, 16, 25, 36. Okay, after 36, 49 doesn't go into 72, and 64 doesn't as well, and then anything past that is greater than 72. So the largest number that's a perfect square that goes into 72 is 36. And I can rewrite 72 as a factorization with 36. So I would write it in the following way. Once you've done that, you can split the radical into 2. And then final step, simplify. So when we say split radical into 2, you're going to have a times b. You're going to split it into the square root of a times the square root of b. So that's what we mean. So this becomes square root of 2 times square root of 36. And square root of 36 is 6. So we got to the same place. So if we can identify the largest perfect square that goes into that number, write that number as a product of that perfect square and whatever number is necessary to complete that, split it, simplify, done. So let's go back to the other examples that we used before. So square root of 405, let's do that. So square root of 405, you'll find out the largest perfect square that goes into that is 81. So I can write 5 times 81. Then we can split. Then we get 9 root 5. We get to the same place. If we did it with square root of 8, the largest perfect square that goes into 8, that's a little easier to identify. It's just 4. Split. Simplify. We get to the same place. Now, how do we identify what's the largest perfect square that goes in? Well, think of your perfect squares. You can use a calculator. You can just do 405 divided by 4, 405 divided by 16, 405 divided by 36. And you can keep trying until you find the largest one, and then you reach 81. When you do 405 divided by 81, you get 5. So therefore, I can write 405 as 5 times 81. So there are 2 methods that you can use to simplify radicals. I will let you choose which one you prefer. I will say that most people prefer that first option of prime factorization. If you are unfamiliar with the perfect squares, I would suggest you go that route.